Hello everyone, I welcome you to another video lesson. In this video lesson, we'll focus on understanding the concept behind correlation and rank correlation. Correlation is a statistical measure which helps us understand the relationship between two variables, x and y. We call them as being correlated if the change in one variable results in a corresponding change in the other. We use the Carl Pearson's coefficient, namely R, to quantify the correlation coefficient between the two variables x and y. This is one of the most popular measures to quantify the correlation, and this coefficient is denoted by R as its value between -1 and +1. Based on the value of R, the correlation between the two variables can be classified as being positive or negative or zero. If the value of R lies between 0 and +1, we say that the two variables are positively correlated. This is observed when an increase in x also leads to an increase in y, or a decrease in x leads to a decrease in y. So both x and y rise or fall together. The value of r is between -1 and 0, and the correlation is classified as being negative. The two variables are said to be negatively correlated. If x increases, y will decrease. On the other hand, if x decreases, y will increase. In this case, we say that the correlation is negative. So when x rises, y falls. When x falls, y rises. If this coefficient takes a zero value, then there is literally no correlation between x and y. That is why the quantification of the correlation is at zero. This correlation coefficient, which we call as Carl Pearson's correlation coefficient, can be determined by one of these three formulae. Even though they are three in number, the concept is the same, which we will explain. If we take the actual data as given in the problem, we have the first formula where we find five quantities: summation of all values of x, summation of all values of y, summation of all values of the square of x, summation of all values of the square of y, and summation of the product of the values of x and y. This is when the actual data is actually taken in as they are given. However, if the data appears to be too large, like more than three digits or so, finding the squares or finding the product of these numbers may become a little tedious. Therefore, we can follow the second formula where we calculate the coefficient based on the deviations from the average. So we determine dx and dy, which are deviations of each observation from the average of x. Dy is the deviation of each observation from the average y. Then we multiply the two deviations, square the two deviations, and use them as a formula. However, if the average is not an integer, sometimes getting the deviation from the average may result in fractions and decimals. This can be avoided by choosing a convenient number, say a, and determining the deviation of x from this convenient choice, a. The same can be repeated for y. We'll choose a convenient number which is as close as possible to the average and find the deviation from that number, say b, and we'll use that as a formula. So we choose the formula based on the observations that are given in the problem. I'll give you an example to demonstrate this choice. We have in front of us these values. All of them are small ones, so we can use the first one as well. Let's check out how that works. Uh, to get a visual representation of how this data happens, we have plotted them on the chart. So the values of x are denoted by blue dots, the values of y are denoted by red dots. We see that they have a similar trend. Both x and y values tend to increase together. Let's find that out. Or you could also equivalently draw lines which connect these plots. And it is obvious that both x and y increase together as it is evident in the chart that we have drawn. Let's calculate the values. These values are small enough, so we can take the values as they are. So we compute summation x, which comes down to 50, summation y, which comes down to 170, x squared added to 308, y squared added to 3270, xy values added to 960. And since there are 10 observations here, we take the value of n as 10, compute the value by using the formula here. The correlation coefficient comes down to 0.7409, which is also reflective of the trend that we observed. The correlation is positive because when x increases, y also increased. That's what we found. Or if you would like to simplify down your calculation, you can try finding the average values of x and y. Here, the average of x is 50 by 10, which is 5. The average of y is 170 by 10, which is 17. So we find the deviations from these averages, denote them by dx and dy, find the squares of dx and dy, find the product of dx and dy. So these numbers come down to 110, 380, and 58. Substituting them in the formula gives us the same number as we got through the method 1, 0.7409. So that means our answer is correct. We have solved that using two methods, and in both cases, the answer is right. We'll take another example. We'll take a data set which has only 5 observations in x and y. Let's try and plot the trend and find out how this happens. Plotting them as points show that they are a little mixed up. And when we connect the dots by the line, we see that they have opposite manners of increasing and decreasing. X decreases, Y increases, which signifies that the correlation between the two, if it exists, should be negative. Let's find that out. And since these are small numbers, we can directly use them. Their squares are going to be small numbers. The products are going to be small numbers. So we just tabulate the values. We see that the x values added to give us 30, y values added to give us 40, x squared values give us 220, y squared values give us 340. The product of x and y give us 214. And since there are 5 pairs of observations, we use the value of n as 5. Using them in the formula, we see that the rank correlation coefficient comes down to negative 0.9192. As the trend was observed, we can see that the value of the correlation coefficient is negative. That makes sense. Now, if you want to minimize the calculation, you can try finding the deviation from the average. The x value has an average of 6 because the sum of all values comes down to 30, and there are 6 observations. There are 5 observations. So 30 divided by 5 is 6. So we calculate the deviations from 6. Y values are to give us 40. So the average is 40 by 5, which is 8. Therefore, we find the deviations from 8. So that gives us dy. We find the squares of dy. We find the square of dx. We find the product of dx and dy. And use them in the formula. We get the same answer, negative 0.9192. So in both cases, the answers are the same, which means we have done them correctly. The next problem is again a very small set. There's only 6 observations this time, and all observations are single-digit numbers. So let's plot them. They are kind of scattered in the plot, and if we connect the dots through a line, we see that x values keep increasing from -9 to -7 to -5 to 5 to 7 to 9. The red line, which indicates the values of x, that keeps increasing. The blue line has its own trend. It first decreases, remains constant, and again increases, and then increases again. So they appear to be kind of not related. So probably the correlation coefficient is a number that is very close to 0. Let's check that. As it happens, when we find out values of x, they add up to give us 0. Values of y, they add up to give us 0. Values of x, y are to give 0. Squares of x give 310. Squares of y give 76. Using them here, we see that our value simplifies down to 0. That just shows that there is no correlation between x and y, which was kind of like available to us through the hint that we got from the chart. For one last problem, let's consider this set of 5 observations in each x and y. Observing the trend, it appears as though x and y increase together. So the value of r must be positive. That's just my wild guess. Let's check that. Here, what we do is we try and find the average. X values give an average of 76 by 5, which is like 15.2. And y value is also close to 50, but it's not exactly 50. But so we calculate the averages from the convenient choices. Let's do the deviations of x from 15 and deviations of y from 50, and we get we call them as u and v just to distinguish them from x and y. Values of u give us 1, values of v give us -2, u square gives us 79, v square gives us 706, and uv gives us 232. Using them in the formula, we see that correlation coefficient comes down to 0.9858. That is also quite kind of making sense because the trend showed that they were increasing together. So it is obvious that the correlation coefficient is positive. And we choose not to use the first or the second formula. We don't use the first formula because the values are kind of large. They are 64, 61, etc. So the squares will involve 4-digit numbers. So to just avoid that large values of squares of x and y, we wanted to find the deviation. But since the average of x and y were not integers, we chose the numbers that are closer to the averages. So we picked 15 as the deviation point for x and 50 for the deviation point for y, and we got the answer. So this one method is enough to give us the answer as 0.9858. On the other hand, there is also a similar measure called rank correlation that is available, especially for observations which are very large. Like I told you, even though there are three different formulae to simplify the calculation, still the calculations involve squaring and multiplying and adding the squares and adding the products, etc. Rank correlation helps us skip through all such time consuming procedures by assigning ranks. So rank correlation is once again another measure to quantify the correlation between two sets of variables, but we do them by assigning ranks. So we do not take the values as they are, but we first assign them ranks. How do we assign ranks? We assign these ranks by sorting the values first and giving the smallest rank to the smallest observation. So we sort the values of x separately and y separately, and we give them the ranks based on their size. The smallest observation gets the first rank, the next smallest gets the second rank, so on and so forth. Here again, when we assign ranks, there may be a possibility where a few observations are repeated. So that is why we have two different formulae. Formula 1, when no observation is repeated and all ranks are integers, which are directly assigned to the observations as per their size. So this formula makes use of only one quantity called as D, where D is the difference between the rank of X and the rank of Y across the table. So we square D and we use them in the formula along with N. However, if there are a few observations which repeat in the data set of X or the data set of Y, we assign the ranks by averaging them. Like for example, there are two observations which are same. Let's say there is a 20 and there is a 20 again. The corresponding ranks are assigned by averaging them. I'll show them using an example. And accordingly, we use the second formula. So this second formula, once again, uses the values such as M1 and M2, where each Mi is the number of occurrences of a repeated observation in the XIR volume. We go to the formula once again when we deal the corresponding problem. So the first problem that I take out is an observation set which has 8 observations. I have first assigned ranks to values of x. Clearly, it is identified that 59 is the smallest observation. So that gets rank 1. 61 is next, that is rank 2. 70 follows with rank 3. 71 is at rank 4. 80 is at rank 5. 81 is at 6. 91 is at 7. And 99 is at 8. We assign similar ranks for the set of observations under y. 105 is at rank 1. 106 is at 2. 110 is at 3. 121 is at 4. 123 is at 5. 134 is at 6. 135 is at 7. And 154 is at 8. Now that the ranks are assigned, we go to the table. So we have the ranks side by side along with the observations given. We find the difference between the ranks. So 5 minus 5 is 0, 7 and 7 is 0, 8 and 8 is 0, 4 and 3 returns 1, 8, 2 and 1 returns 1, 6 and 6 gives us 0, 3 and 4 gives us negative 1, 1 and 2 also gives us negative 1. And then we find the squares of d and we add all the squares, we get the value as 4. Now, once we have d squares adding up to 4 and n adding up to 8, because there are 8 observations, we can use the formula that we saw 6 times d squared, that's 6 times 24 on top, and 8 times 8 square minus 1, that's 504. Dividing 24 by 504 and subtracting that from 1 gives us the answer as 0.9524. Now, the benefit with this method is that we do not take the exact values, we only take their positions based on ranks. Of course, it is a matter of convention that we assign the smallest rank to the smallest possible value. It can also be reversed. The topmost rank, namely the first rank, can also be assigned to the observation, which is the largest. So, contrary to what we saw in the previous slide, we can also assign ranks such that the largest value gets the top rank. It doesn't affect the final answer. For example, let's get back to the same data and we can see that 99 is the largest observation among the values in the X data set, and 91 is the second largest. So we can assign ranks even after sorting them in the descending order. This will help us assign ranks again. We can repeat the same for the data set Y, with 154 being the largest. We can assign it the rank 1, followed by 135, which is rank 2, so on and so forth. We'll get 8 ranks as usual. As long as we follow the same convention for assigning these ranks, the end results will not change. So we have once again drawn up the table for the ranks for X and Y. We have found the differences. We have squared the differences and we added up the squares. The answer comes down to 4. The same 4 that we obtained while we assigned ranks in the other fashion where we sorted them in the ascending order. The same total is obtained even after we sort them in the descending order, and hence the coefficient of rank correlation does not change. As long as we follow the same convention for both x and y, the choice of the order, be it the ascending order or the descending order, does not affect the answer. The answers will remain the same. Now we'll just go to another problem. Let's look at this problem considering two sets of values x and y, each having 8 observations. Here, though, we find that there are numbers repeated. In X, 57 and 58 get first rank, first and second ranks respectively. But for the third rank, there is a tie. For the third rank, we see that there are two observations which are at 59. So we choose to average the ranks. So the third and fourth rank are average. So 3 plus 4 by 2, that gives us 3.5. And then immediately after 59, we have 260 values. So there is a tie for the fifth rank. For the observation 60, we add up 5 and 6 and calculate the average. That's 5.5. So both 60 values are assigned the ranks 5.5. The next rank is at 61, which is rank 7. The next rank is for the observation 64, which is given 8. For y though, we do not have a problem because all values are distinct. 95 takes up rank 1, 97 takes up rank 2, 106 takes up rank 3, 108 takes up rank 4, 110 takes up rank 5, 113 takes up rank 6, 120 takes up rank 7, and 126 takes up rank 8. Having calculated the ranks, we proceed further and calculate the differences. So the differences are calculated as D, and we also find the D square values. D square values added to give us 24. However, since there are observations which are repeated, which led us to averaging the ranks, we use the second formula. So for the second formula, we need D square, which is the 24, and we also note down what are M1 and M2. M1 and M2 actually denote the number of occurrences of any observation that is repeated. We see that 59 appears twice, so M1 is at 2, and 60 also appears twice, therefore M2 is at 2. We find M1 times M1 square minus 1, which is 2 times 3 at 6, and M2 times M2 square minus 1, which is also 2 times 3, which is 6. Once we know these numbers, we go to the formula. The 6s are added to give 12. 12 is divided by 12 to give us 1. And this 1 is added to d square, which is 24. So this 25 is multiplied by 6 divided by 8 times 8 square minus 1, which is 504. Simplifying, we see that the value of the rank correlation coefficient is at 0.7024. Again, for this problem, we have the two choices of sorting the observations. We can do them in the ascending order as well as the descending order, as long as we are consistent with the convention that we do. So, in the previous slide, we assigned ranks, we're sorting them in the ascending order, and we've got these observations for R. We could do the same here. We can sort them in the descending order. We can see that 64 takes up the topmost rank, being the largest value. 61 is again the second rank. There is a tie for 60, which will mean that we average ranks at 3.5 and 3.5. And again for 50 at 5.5 and 5.5. And we can again complete assigning the ranks to the observations in the data set Y. Repeating the same, we complete assigning the ranks to the data set X. Repeating the same with the observations in the data set Y, we observe that 126 is the largest value assigned at first rank, followed by 120, 113, 110, so on and so forth. This gives us the ranks 1 through 8. We drop the table, we assign the ranks, we calculate the differences, we square the differences, and we see that the same total is obtained for the sum of the squares of D. The 24 that we obtained while choosing the ascending order is also obtained when we choose the opposite descending order. The values of M1 and M2 do not change. Substituting them into the formula will give us the rank as 0.7024 because the squares add up to 24. M1 times M1 squared minus 1 gives us 6 on both occasions. We add them to 24, that's 25. And we multiply it by 6 and divide by 8 times 63, giving us 504. The coefficient of rank correlation can be obtained as 1 minus 0.2976, which is at 0.7024. So this sums up the two different types of correlation coefficients. One by taking the exact value, and two by taking the ranks assigned to these observations. So this way, we are able to quantify the correlation whenever it exists between two sets of data. and we can also choose the corresponding method based on our convenience. I hope you found the video interesting. I'll follow this up with another video lesson very shortly.